chemistry, for example, in terms of phase transition from one phase to another. Okay? And we have in semiconductor non-metallic material that conduct electricity, and so to do that, you are using the thermal excitation electron across the band gap. So in semiconductor, remember the magic number here, 0.1 electron volt. Electron always have this 0.1 electron volt as its fingertip due to the temperature. So the electron is always moving with this type of energy that you can bridge the band gap, across the band gap, and therefore make electronic transition from the valence band to the conduction band. If you can have enough energy with 0.1 eV, right, you can move across, and then you would have conduction. And there are, of course, different type of semiconductor. People heard about this. There's negative type or N-type semiconductor, which means that you have more electrons in the conduction band than the ion in the valence band. So the negative electron is the current carrier. Okay. So the situation is like this. So here is a flow charge that this is my Fermi level right in the middle, right in the middle. And if I move this bunch of electron across my band gap into the conduction band, right, we have a little bit of this, right. Usually, remember our definition of semiconductor is that you have a partially, largely filled or largely empty band. So this is a largely filled valence band, right? And this is a largely empty conduction band, okay? So this is not largely mean about 90% of that is filled. So this is a Fermi energy level. So this is a normal semiconductor in this way. Now, if you dope it so that you can create more so-called create a negative type semiconductor, so you inject or you create some material dopants so that you have extra electron, so to speak, extra electron in your material. The electron has to go somewhere, so the electron get shifted into more electron is in the conduction band, because this is where it's populating. So in effect, you have skewered your Fermi Dirac distribution this way, and the Fermi level has shifted a little bit closer to the conduction band. Okay. Or you can dope it in a different way. You can dope it with some material that are poor in electrons, more electron deficient. So like boron, for example, you dope here with phosphor, for example, then you have N-type boron. You get P-type or positive type, because boron is has less electron than silicon. So in fact, you create a deficiency, less electron inside your bulk, the majority of the bulk of the silicon that you have. So you got more negative hole in here. So the Fermi level skewer towards the low energy in the case of P-type, or towards the valence band, like this. Okay. So then, if you skew like that, then what happens is that in effect you have a P-type semiconductor which has more positive hole, so-called more positive hole in the valence band than electron in the conduction band. So the positive hole is the primary carrier, right? So what? So sometimes when you talk about positive hole, how does positive hole actually carry charge across? Okay, so this is often an interesting question, because we understand, as chemists, we understand we can move the electron, but why positive hole can be a charge carrier when we talk to the electrical engineer, for example, right? It's rather easy to understand. So I think, let's see if we can describe this a little bit. Suppose you have a material and you have mostly neutral material, and you have a few material that are positive charge, right? In other words, you have some empty orbital. Think of it as empty orbital, right? So they are called hole like this, right? Let's say they are located in this region, and so now you have the normal normal material like silicon. This could be boron or something. Silicon is distributed on this side with fully charged electron, no electron deficiency. So here you have more electron than this guy here. So in fact, you have a positive charge or hole, so-called hole. So what you got is that you then when you apply a potential, for example, then what will happen? The electron will move from here to fill up this hole, right? To make this now, what happened then is that now this guy is satisfied. So this is now fully full like that, right? And what happened to these guys that move the electron to that way? The electron now you become positive here because you are losing electrons, right? From this. So this becomes the hole, right? So in fact, the electron is moving this way, right? You can see the hole, which is my positive charge, is actually moving in the opposite way as you apply this. Okay, so it's the same phenomenon. You can move hole, or you can move the electron. The electrons still move, but it's just how you talk about it. So here you can see that the electron, the hole are moving this way, but the electron actually transfers over this way. Okay, so that's how we understand when we talk to the electrical engineer, they talk about holes. What is hole, right? Hole is actually a positive charge, and so you move it in the same way, except in the opposite direction. And in the case of lattice, of course, only the electron move, your atom don't move, so you have hopping, this electron hopping across your material, and the hole goes this way. Okay? So I think we can understand how the electrical engineer talk about this, or solid-state physicists when they talk about this hole transfer, or electron transfer, and dopant, quite importantly, create an imbalance in here. So you can change this Fermi level by doping differently. You can see that Fermi energy is moving about as you dope the material differently. Okay, and sometimes this is known as band gap engineering. That how you dope material in your semiconductor. So you can buy material with different dopant. There's a lot of industry out there that supply you with different dopant material to dope the material so that you can get the appropriate Fermi energy that you want. Okay, next I'd like to go into a little bit more detail about how you get to this. A little bit mathematics perhaps, so bear with me on this part, and you may need to go back in first year chemistry to read up a little bit on quantum mechanics if you don't have this. But don't worry about too much about it. I think the whole idea of this part of the lecture is that I want to make sure people understand that there is firm physical basis in deriving these equations and the origin of the band gap that you have. Okay. So what I like to do is to tell you a little bit about free electron gas model, right? So, and then I like to talk a little bit about particle in a box, both in one-dimensional box and a particle in a double one-dimensional box, two one-dimensional box, as a way to sort of give you some firm basis, if you like, to see how the mathematics arising to give you this band gap structure that you see. Okay, so I think it's kind of useful. If you don't know, if you haven't done quantum mechanics, don't worry about it. Hopefully you can follow based on a couple of basic quantum mechanics principles that you see. And I won't derive the equation. I just give you the results so that you can see the evolution of this thing that comes about. Okay. So I say this is important to understand a number of important physical properties of simple metals like lithium with one free electron, right? Sodium, and so forth. in terms of so-called free electron gas model, right? What is a free electron? You heard physicists talk about these things. And in this model, what happens is that the weakly bound electrons of the electron move freely in the volume. So it's like a gas, right? It's like ideal gas particle, right? We learned about this in first year chemistry. You treat the particle as non-interacting, right? In this case, you treat this electron inside your lattice of lithium, let's say, right, as free electron, meaning that they're not being held back by any potential of your atomic core, right? They just move freely. They are not interacting with your atomic positive core lattice, right, which is your lithium nuclei, right? They don't care about that. So it's very much like the ideal gas model for electrons.